Hi, I welcome you to this session on Axial Flow Compressor. In the last couple of classes, we have understood a few numericals on Axial Flow Compressor. So in this session as well, we will solve one more numerical on Axial Flow Compressor. And I believe if you can understand all the three numericals, you can solve any type of numerical with respect to the axial flow compressors. You need to revise all the concepts multiple times to get familiarized with the methodology of solving these problems. Okay, let's begin. So the problem states an axial flow compressor of 50% degree of reaction has blades with inlet and outlet angles of 45 degrees and 10 degrees respectively. The compressor is to produce a pressure ratio of 6:1 with an overall isentropic efficiency of 85%. When the inlet static temperature is 37 degrees Celsius, the blade speed and axial velocity is constant throughout the compressor. Assuming a blade speed of 200 meter per second, find the number of stages required if the work done factor is 0.1 and 0.87. Right? So this is a unique problem where the work done factor is given, one for ideal case, another for real case, and we need to calculate the number of stages required for a axial flow compressor. Right? So let's start and look into how to solve this problem. Right? So again, we start with the temperature rise in a stage. On the right hand side, we have the work done factor, the peripheral velocity, axial velocity, and the CP, that is specific heat at constant pressure. Then we have tan beta 1 minus tan beta 2, that is in terms of blade angles. From CA, if assuming that CA remains constant, so I can write CA as U by tan beta 1 plus tan beta 2. Again, these equations are derived in the previous sessions, please go through that. Just substitute the values. I know the value of peripheral velocity, that is 200, beta 1 is known and beta 2 are known. So just substitute and get the value of axial velocity as 170 meter per second. Right? So once we get the axial velocity, we'll move on to calculate the number of stages required for different work done factor. So let's start with work done factor 1. So if the work done factor is 1, the change in temperature per stage is calculated using this equation. Let's call this as equation number 1. So using equation number 1, you just substitute all the values, and the temperature rise in each stage is given as 27.8 Kelvin. Because I know the value of U, CA I just calculated, beta 1, beta 2, and the CP value 1005 joules per kg Kelvin. And with this value, so I'm going to get the temperature rise in each stage as 27.86 Kelvin. Now we will calculate the overall temperature rise with the help of the isentropic efficiency equation, and just substituting the values of the inlet temperature, the isentropic compressor efficiency, and the gamma and the compression ratio as 6. I get the value of overall temperature change as 244.1 Kelvin. Now this is a very simple method. I know the rise in temperature for one stage, and I know the rise in temperature for the overall stage. Right? So what are the number of stages? You just have to divide the total temperature rise by the stage temperature rise. Right? So I get the total number of stages roughly as about 9. Right? 9 stages of compressor blade rows are present. Then I can compress the air to 6 times if the work done factor is assumed to be 1. Right? So that is the meaning of this 9 number. Right? So next we will try to understand if I change the work done factor to 0.87, how the number of blades will change. Now this is a realistic value. Right? Work done factor exists in all the real flows. So assuming it has to be 0.87 is a good assumption. Right? So then again we will follow the same procedure. Temperature rise in each stage. So we got it as 24.24 and the overall temperature rise will remain same, and if I divide one by the other, I get the number of stages as 10 stage, right? So here one very important point you need to understand is, if the work done factor is considered for a real flow, then the number of blade rows are going to increase, right? Compared to the previous value, that is 9 is the number of stages required to compress the air 6 times if the work done factor was 1. In the next analysis, we understood that the number of stages required will be 10 to compress the air by the same pressure ratio, that is 6 times, and with the work done factor of 87%, right? So please understand. So ideal case, you need 9 blade rows to compress the air 6 times, but in real case you need 10 rows to compress the air to the required pressure ratio, right? So this is the understanding we get from this numerical. It is very interesting and practically relevant, right? So with this we will end the numericals of axial flow compressor, and we end the analysis of axial flow compressors as well, right? So in the next session we will start with the centrifugal flow compressor, and we'll try to analyze different parameters that are in the centrifugal flow compressor, right?